Alright, this is video 2 in the never-ending series of stoichiometry examples. Again, this is going to be a pretty straightforward one. The basics of stoichiometry: compare what you have in moles for our reactants to get a limiting and excess reactant, get an amount excess by subtraction, use the limiting reactant compared to your products to get a theoretical yield, and if you need to, get a percent yield. So there's 4 basic steps. And if you do these steps, that's basically every single stoichiometry problem possible, laid out in a very clean and efficient way. I started out by already completing and balancing an equation, and I already gave these given amounts, and I know it's impossible to read because I took that purple highlighter, but we'll see those as we go. All right, so there's our recipe. These are our ingredients that are given, and then these green numbers here are molar masses, periodic table, and then add up 2 aluminums and 3 oxygens on the periodic table. All right, so we need to get moles for each reactant because our chemical reaction gives us a mole ratio, in this case 4 to 3 to 2. So I'll take my 362.1 grams of aluminum and my 214.7 grams of oxygen. Now those are grams. I want to get them to moles. You divide by molar mass, and I happen to take a note of that, 26.98 grams per mole and 32.00 grams per mole. Again, those numbers are coming from the periodic table. Oxygen 16, 2 of them is 32. All right, this is going to give us what we have. And this step seems trivial, but this is a critical step, literally writing the word have, and then correspondingly over here, we will literally write the word need, because that's going to tell us how much we have of each and how much we need of each to figure our limiting reactant and our excess reactant. All right. So in this particular case, our numbers end up 13.42 moles of aluminum and 6.71 moles of oxygen. Okay, that's what we have, and we need to figure out what we need. We'll do dimensional analysis to get there, comparing our reactants to each other using those coefficients from the balanced chemical equation. Moles of aluminum, so there's 4 moles of aluminum for every 3 moles of oxygen. All right, moles of oxygen, 3 moles of oxygen for every 4 moles of aluminum. And let me say this again in slow-mo. First box is what's given. Everything after the first box comes from the balanced chemical equation. And again, right now we're just comparing our reactants to each other so that we can figure out how much product can be made. This is 10.1 moles of oxygen that we're going to need, and 8.95 moles of aluminum. All right. Now, I've mentioned before I'm very easily distracted, but the good news is, like, when I just got distracted, I can look and say, all right, I have and I need. Have 13.42 of the aluminum, need 8.95. It's continually a hurdle for people to overcome to compare diagonally, but the short of it is, to use up this much oxygen, I will need this much aluminum. So that's why I'm comparing this number here, my moles of aluminum, to what I actually have. To use up all of this, I will need this much aluminum. To use up all of this, I will need this much oxygen. And as we look here, obviously, I have 13.42 moles of aluminum. I need 8.95. That's got to be our excess reactant. And I will, I guess, circle it. That is our excess reactant. And I have 6 and I need 10. I don't have enough. That's our limiting reactant. So we've checked our first step off here. Compare the limiting and, compare the reactants to each other to find the limiting and excess. Our next step, whether we are asked to do it or not, I think it's useful, is to find the amount excess. And I just need to look here. I have 13.42 moles of the aluminum, my excess reactant. It's just the have minus the need, right? I have 13.42 moles of aluminum, and I'm going to subtract the 8.95 moles of aluminum that I need. In this particular case, we end up with 4.47 moles of aluminum excess. And we will multiply that by the molar mass to turn that into grams. You don't have to. Like, if you can get moles, you can always get grams, but I'll do these steps just so you see them and you get in the habit of doing them. So, and actually, like I mentioned in a previous video, it's going to pay off. We'll multiply by 26.98 this 4.47 grams per mole. And again, your 26.98 is coming from right there. That's from the periodic table, turning moles of aluminum. And we end up with 120.6 grams of aluminum excess. All right, so this is a useful number for us. Should have done that in brown, but we'll live. So, things that we have found out so far, we identified our limiting reactant and excess reactant, and we got an amount excess. That's two of the things we were looking for. Now I'm going to go back. That was my limiting reactant. I'm going to use that to figure out how much product I can make to get a theoretical yield. So I will divide this out here. I guess we had like a 1 and a 2, and this will be 3. We have, in this case, 6.71 moles of oxygen. And I do want to distinguish. Here we compare just the reactants because we need to figure out which one matters. Here we compare one of the reactants, the limiting reactant, to our product or products because that's going to tell us how much we can make. And it is dimensional analysis. Everything after the first box comes from the balanced chemical equation. That's 3 moles of O2, and those have to match there to cancel out. And that's going to be for every 2 moles Al2O3, aluminum oxide. Okay? In this particular case, we end up with 4.47 moles of aluminum oxide. 4.47 moles. That's how much we could have made, theoretically, maximum, right? Now, whether or not we made that is a totally different story, but that's how much we could have made. And we'll multiply by the molar mass here, which was 101.96. And again, I added up the pieces. 2 aluminums and 1 oxygen. Sorry, 2 aluminums and 3 oxygens add up to that. So I'll multiply by 101.96 grams per mole, and we'll end up here with 456 grams of Al2O3. 456 grams Al2O3. That is our theoretical yield, the maximum we could have made. And that leaves a percent yield, and in order to get a percent yield, we need to be given an actual yield. And our actual yield was given right there. And what the actual yield is, it's when this experiment is done in a lab somewhere, that's how much they collected, all right? And it's possible to calculate over 100%. By the law of conservation of mass, you can't have over 100%, but somebody could screw up in lab and give you a bad number that would calculate as over 100% yield. But anyway, it's not going to happen here. Actual yield has to be given. It's some number somebody came up with in the lab. Excuse me, it's freezing in my garage today. So to get our percent yield, it's just our actual over our theoretical times 100. Luckily, I've labeled everything, right? Like, oh, there's my theoretical yield. In this case, there's my actual yield, 313 grams of Al2O3. Could have made 456 grams of Al2O3 multiplied by 100. And that's going to give us 68.6% yield. And we'll highlight that to indicate that this number has paid off as well. Now comes the step that should be very important on your priority list, and that's the step of, did I do it right? And we can check it. And I think that's part of what's so important, laying things out in a clear and logical way so anyone can look at what we did and figure out or see what we did, and then check it in the end. It's a very, very useful tool to be able to do that. And using the law of conservation of mass, what we start with has to be equal to our end mass. And so our starting mass is just our reactants. And our end mass is our product plus any excess. And that's the key there, is that amount excess. And I realize we're sneaking down on the page here. So let's see if we did indeed calculate what we said. Our starting mass was 362.1 and 214.7 grams of oxygen. And then our ending mass has to be the 456 grams of aluminum oxide plus our 120.6 grams of aluminum excess. And on this side, we end up with like 576-ish, 0.8, I guess. And on this side, we end up with 576.6, which is pretty darn close. And within sig figs and everything else, that checks. So that is how that works. I will set up the next problem. This problem is a little special, and you'll see why in a minute. But let's start out with this information again. You have to have a completed balanced chemical equation. I already filled in some molar masses. Magnesium 24.31 from the periodic table. Nitrogen 28.02. There's two of them, 14.01 times 2. And then 3 magnesiums and 2 nitrogens adds up to 100.95. So that's where those green numbers came from, a little preliminary work. There's our completed and balanced chemical equation, and here's the information that might be given. It's kind of artificial for me to just list things in that way. And in some future examples, we'll go through the different wording and how these problems might look in a textbook setting. But for right now, we're just going through the basics of these skeletons, all right? And we have to take this information, turn it into moles to compare so we get our limiting reactant. We'll do some subtraction to find our excess. We'll compare the limiting reactant to our product to get a theoretical yield, and then we will get our percent yield since we have an actual yield there. And as I said, there's going to be one little surprise as things go here. We'll start out with our 204.2 grams of magnesium and our 78.5 grams of nitrogen. This is a side reaction in a common laboratory example. So a lab that a lot of first-year chemistry classes or college chemistry classes do is they take magnesium metal and they burn it in a crucible under controlled oxygen. They open the lid just a little bit. But air has nitrogen as well, and when you get things super hot, side reactions can happen that you don't expect. So magnesium and nitrogen actually can make magnesium nitride. And some of the other examples I did, one of them is how you get rid of that. Turns out if you add water to magnesium nitride, you get magnesium oxide and ammonia gas. So this is a real example, or this is a real reaction that happens as a side reaction in one of the labs we do. Magnesium 2431. Again, that's from the periodic table. And nitrogen 28.02. And again, that's 2 times 1401 from the periodic table. Okay? I realize it makes you feel like a toddler to write the words have and need. Do it. All right? It gives you the opportunity to get lost and come back and know where everything is, and it makes it very logical why you're comparing the things that you do. In this case, we end up with 8.40 moles of magnesium and 2.80 moles of nitrogen. All right, we will do our dimensional analysis here to figure out which one of these we have too much of and which one of these we don't have enough of. In this first case, 3 magnesiums, right? Everything after the first box comes from the balanced chemical equation. 3 moles of magnesium for every 1 mole of nitrogen. And so, little division, you end up with 2.80 moles of nitrogen that we need. And that may be setting off an alarm for you right away. Okay? 2.80 moles of nitrogen, again, everything after the first box comes from the complete balanced chemical equation. 1 mole of nitrogen for every 3 moles of magnesium, right? In this particular case, 8.40 moles of magnesium. This is a special situation that's totally possible, right? You have 8.40 moles of magnesium, and you need 8.40 moles of magnesium. Hey, I have exactly what I need. And reasonably speaking, you have 2.80 moles of nitrogen, and you need 2.80 moles of nitrogen. You have exactly what you need. That is very, very, very important. And when that happens, we call that stoichiometrically equal amounts, all right? So for both of these, the have equals the need. We have exactly what we need. We have exactly what we need of each reactant. It's like going into your pantry and exactly having the ingredients for a batch of cookies, which is ridiculous, right? But it's, I guess, a possible scenario. So what is this called? We call this situation stoichiometrically equal amounts. where you have exactly what you need. And in that case, there's technically no excess reactant. I'll put that in quotes. Sorry, yeah, no excess reactant. And there's no limiting reactant. And when I say no limiting reactant, that means that either can be used to calculate the products. All right, so we don't have an amount excess. I can use either of these amounts to find out how much product I can make because they're both exactly what we need. So I'm going to say we have stoichiometrically equal amounts for addressing step 1 there. For step 2, to get an amount excess, we don't have any excess reactant, so there is no excess reactant. And I guess if we're going to lay this out like that problem over there, there was our 1, setting that up. And there was our 2 right there, where we established there was no excess reactant. And we'll go on to our third part here, which is getting a theoretical yield. We use our limiting reactant. In this case, it doesn't matter. I'll just go with the first one, 8.40 grams of magnesium. And we know from our balanced chemical equation, for every 3 moles of magnesium, there's 1 mole of magnesium nitride. So 3 moles of magnesium. Again, I know to put that there. Oops, wow. See, dimensional analysis. For every 8.40 moles of magnesium, there's 3 moles of magnesium for every 1 mole of our product, Mg3N2. And so we end up with here 2.80 moles of magnesium nitride that we're expecting to make. And that makes sense because it is a 1:3 ratio, exactly how the nitrogen was, and we came up with needing 2.80 moles of nitrogen. So given 2.80 moles of nitrogen, we would expect to make 2.80 moles of magnesium nitride. So that's set up right there. This is our theoretical yield. We can multiply, in fact, let me do that in a slightly different color here. We can multiply that by its molar mass that we calculated in advance, which is 100.95 grams per mole. And we end up with 282.7 grams. As our theoretical yield. And impressively, I screwed up my color coding again. But we'll live. That is that. And we can do this last part, this percent yield, just by taking our actual yield, 47.1. So that's a number you'd have to be given. It's something somebody made up in lab. I made it up entirely. But our percent yield is supposed to be our actual over our theoretical times 100. We just grab those numbers as given. In this case, 47.1 grams. We divide by our theoretical yield that was 282.7 grams. And we end up with a 16.7% yield. Now, one of the things we're going to note in future videos is that percent yield describes how much product you made of one thing, and when you have more than one product, it describes how much you made of all the other products as well. So that's a super important idea. Now, this last step, and again, I think this is fairly critical, or at least fairly useful, is doing a quick check that what you have is, sorry, what you started with is what you end up with, right? So in the beginning, we started with 204.2 grams of magnesium and 78.5 grams of nitrogen. And in the end, that should equal, since we have our yield, our theoretical yield, plus our excess. In this case, our excess was 0 because we had stoichiometrically equal amounts. Our yield was 282.7 theoretically, grams of Mg3N2. So mass of stuff you started with should be mass of stuff you end up with plus 0 grams of excess. And so 204 and 78, this gives you exactly 282.7 in fact. So this does check. There's a good chance we did it correctly. All right. So this is our second and third stoichiometry example. Like I said, there's 18 and we're going to work our way up.